Good afternoon, everyone. Welcome to the STRIDE webinar on smartphone-based incentive framework for dynamic network level traffic congestion management. I am Rupa. I'm a PhD student at Georgia Tech, and I work with Dr. Srinivas Peeta. He is a professor of both civil engineering and ISYE at Georgia Tech. We also work in the Autonomous and Connected Transportation Lab at Georgia Tech. Today's webinar is sponsored by the STRIDE Center. STRIDE is a 2016 US DOT Region 4 University Transportation Center. We are a consortium of 10 Southeastern colleges and universities, with University of Florida leading the team. The mission of this UTC is to develop novel strategies to reduce congestion, specifically urban congestion. And should you guys have any questions throughout the webinar, please feel free to add them in the chat. Once we are done, we will get to the questions right away. And let's get started. So the problem that we're trying to address with this project is reducing urban congestion levels, specifically within the US. If you look at the average American, they spend about 100 hours in congestion as of 2018. And not only that, there is a loss of time, we have an economic cost to the congestion. On an average, an American spends about $1,300 stuck in congestion as of 2018. Beyond the economic cost and the time value, there is also effects on the environment. 27% of greenhouse gases within the US come solely from the transportation sector, making it one of the leading contributors. So to tackle this congestion issue in urban areas, there have been both supply side solutions and demand side solutions. If you look at the supply side solutions, these typically involve new infrastructure or increasing capacity to existing infrastructures. Whereas on the demand side, we have more of a user behavior change solutions. These are typically tolls, congestion pricing, or incentives. These solutions typically come with their own ups and downs. On the supply side, building new infrastructure can be extremely time consuming and expensive, not to mention at the end of the build cycle, it might not deliver the results that we want them to because the demand has increased by then. On the demand side solutions, we have tolls and congestion pricing typically implemented throughout the US. This is asking users to pay additional amount to use public good, which can make it inequitable for a large population. And on the other side, there is incentives, which is paying users to promote a certain kind of behavior. That will be the focus of this work. And if we look at literature, specifically in the domain of incentives and travel behavior, we have a lot of research studies over the past 20 years, but most of these studies are less than 1 year long, and they typically are in a research context, providing incentives for a certain time and taking them away. Longer term behavioral change was typically not studied. And beyond that, the design of incentives is not studied as rigorously as design of tolls or congestion pricing has. The information delivery or incentive delivery is typically through websites and smart physical passes. Over the last couple of years, as smartphones became more accessible and developing became more accessible, there have been smartphone apps, but not too many. And if you look at industry context, transportation-based real-time information provision apps have been widespread across the US and specifically across urban areas. We have industry leaders like Google Maps and Waze that provide real-time information and trip making with either pool data or sensor data, but neither of these typically target behavioral change. A recent update in Google Maps suggests a more eco-friendly route, but the way the routes are calculated, the way the eco-friendliness is calculated is not known. So they do not typically target behavioral change and target behavioral change that reflects in system level conditions. So the objectives of this work is to develop a solutions framework to address urban traffic congestion using behavioral change strategies, specifically positive behavioral change strategies. and later model these strategies in the context of dynamic traffic assignment and understand the effects it has on a network level. This study is only addressing route choice behavior, but the concept can be applied to both mode choice and departure time choice as well. In terms of the behavioral change strategies, we are primarily looking at two: tangible incentives and nudges. Tangible incentives are any economic incentives that motivate or drive any individual to do something a certain way. In the context of route choice, it is adding economic incentives to each route or each link on the road network. By doing so, we can ensure that the incentives on each link are time-based, that is, they are based on the time of the day. They are dynamic, that is, they change throughout the day. They are system level, that is, they are responsive to system congestion levels and congestion on the road link. And they are also geographical because they're on each link. The second strategy that we're using is called nudge. It comes from the nudge theory developed by Taylor and Sunstein. It is any aspect of choice architecture that alters people's behavior in a predictable way. A typical example of a nudge is when you go to a grocery store, you see and pick the item at your eye level. By placing a particular brand at an eye level, they're nudging you to use that brand. Another example is if you use Google Maps to make your trips, you more often than not choose the first option or a default option. Whatever they put as a default is a nudge, is nudging you to use that choice. So the usage in this context is order of trip options within a route choice. Nudges are personalized to user. The default option can be different for different users, depending on what their preferences are and what their value of time is. The real-time smartphone-based incentive framework that is proposed uses a mobile app as the forefront of the structure, where it is providing users with incentives, tracks users' choices and preferences. The incentives themselves are generated on real-time, based on real-time congestion levels of the network, and are provided to each user. The routes that the user chooses are fed into a user preference model that affects traffic and also is used to design the nudges. And a critical part of this framework is to generate real-time incentives. And to generate real-time incentives, we are going to use a reinforcement learning-based method. A reinforcement learning-based method has an agent and an environment. The agent acts in the environment to change it, and it modifies itself based on the reward. So in this context, our environment is the traffic environment or traffic network. Our state is congestion levels. It's looking at the congestion levels and trying to add incentives onto the network so that the system congestion levels are changed. So our action is updating incentives in real time based on system level congestion. The reason we use a reinforcement learning based method and not any analytical solution is because a reinforcement learning method can be trained offline and deployed online, which reduces the computation burden and allows us to stay in the real time. It's also sequential and time-dependent data. So we are using a reinforcement learning framework and not any other kind of machine learning framework. Analytical models can get computationally intensive, especially when implementing it online in real time. So to formulate the state, it needs to be a representation of the system conditions. So since we are trying to tackle congestion, the state the reinforcement learning agent considers is travel time on every arc. It's a set of travel times on every arc in each time step. Because the agent is trying to update incentives, the action it takes is generating incentives on the network. These can be present on all arcs or links of a network, but it doesn't mean it has to be present on all edges. It depends on the congestion levels. Some edges might have incentives, some might not have incentives. And incentives are positive values as opposed to tolls or congestion pricing. A reinforcement learning agent maximizes its reward. It acts on the reward it gets and it wants to increase it. So this should align with our overarching goal of reduction in congestion. So we want to reduce congestion. So the first part of our reward function is a sum of all travel times on all network. Secondly, we also are considering economic incentives. So that costs money. So there is a budget constraint included in the reward function that is a sum of all the incentives. So overall, since these two are negative values and we want to maximize the reward function, there is a negative sign before both of these. So it is minimizing the travel time and minimizing the amount of incentives used. This is how reinforcement learning agent generates the incentives. To be able to train this agent, we need an environment that can not only simulate a traffic network, but also simulate user preferences. So we are using a user preferences model that has a utility function, which weights both time and incentives for its route choice. And in its decision making, we are considering two types of decision making. First is habitual users. These are the users that even if the cost of a different route is lower, they're not going to take the route because they're comfortable with what they have right now, and there is some resistance to changing the route. And the second type of users is nudged users, where even if the cost is a little higher, the user takes the route because they are nudged to do so. And the reason why we're considering these two is because we are using nudge as a behavioral change strategy, and we want to model the effect a nudge has on users. In terms of the training environment, we are using a microscopic traffic simulator. It is there is an open source simulator called Sumo that we are using to generate traffic movement. The users are generated as individuals in that environment, and the decision making follows either habitual or nudged users. The user preferences are fully assumed in this context. The reinforcement learning agent uses a policy gradient method, and it takes in state value or travel time as the input and generates incentives on the network. We have trained this in multiple stages of app penetration level. Since it's a mobile app-based framework, we can't assume everyone has the app. So we are looking at multiple levels of app penetration, and in this case, app penetration corresponds to percentage of users equipped with the incentives provision app, and that can change the route. All other users are assumed to not change their routes. The reward value is higher under 100% app penetration level, showing that there is improvement with incentives and increased app penetration level as everyone is on the same system. But as we can notice, all scenarios yield similar training curves. This could mean that the RL framework needs more training, or that there isn't enough congestion to tackle on the network. We have used a test network of Hanover Suite, and the congestion levels are typically lower in that test scenario. For the stakeholders, the stakeholders for this product are city managers or traffic managers. With an input of daily travel patterns of the city and socio-demographics of the population, they will be able to train the same reinforcement learning model and implement it should they have the infrastructure. The reinforcement learning model needs to be trained anytime there is a change in the transportation system. For example, there is an additional road, increased capacity, or any changes to the system itself. And when city travel patterns change, if there is a drastic event where that shifts the travel patterns of majority of the users in the system, that is an indication for you to retrain the model offline. This study also assumes full knowledge of each user preferences. That is, we assume how users prioritize travel time and incentives and how they choose in between. Should a stakeholder implementing this framework needs to estimate these values ahead of time so that they can feed it into the training environment. The RL model currently that is implemented was for a small test network of Hanover Street. And to implement this on a larger urban network, say city of Atlanta, it can get computationally intensive. In such cases, transportation network can be broken down into separate sections and trained using a multi-agent reinforcement learning model. There is a multi-agent variant of the deep deterministic policy gradient algorithm that we've used, and that can be extended to such cases. That is all for my part of the presentation. Do you want to share your screen and start yours? Hi, you're muted. Can you unmute? Yeah.
Yeah, sorry. Hi, everyone. Thank you for coming to the webinar. In the second half of the webinar, we are going to present a correlated equilibrium-based routing mechanism with distributed solution algorithm. The routing mechanism could mitigate traffic congestion and minimize system cost, while it doesn't conflict with individual traveler's selfish nature. The distributed solution algorithm helps to conduct the routing mechanism efficiently in a real-time manner with the help of the computation power from individual travelers' smartphones. The proposed routing mechanism and solution algorithm can be implemented as an app on drivers' smartphones. So I'll start with the motivation and introduce what problem this project tries to address. Oh, it stuck. Sorry. With the rapid development of wireless communication, mobile computing, and GPS technologies, drivers nowadays are relying more and more on navigation services. A survey in 2018 shows that 77% of drivers regularly use navigation services to look up directions. However, navigation services and real-time traffic information does not always lead to better traffic conditions. In the currently most widely used independent routing, drivers use real-time traffic information to make routing decisions independently and selfishly. This is what we do now in our daily lives when we use Google Maps or Apple Maps on our cell phones. In most cases, we just quote the travel time for each route and choose to take the fastest route. However, such selfish reaction may lead to the overreaction and flash crowd effect. So imagine when a group of drivers receive similar traffic information, then most of them will have high probability to choose the similarly fastest routes. And in the graph, it is the blue route. So as a consequence, that route may become congested later when a large number of drivers arrives, which results in new congestions around the route. Such overreaction effect makes independent routing systematically inefficient. On the contrary, there is a system optimal routing, in which there's a system planner chooses routes for all drivers to minimize system cost. This is the ideal scenario transportation researchers want to achieve. However, it is difficult to be implemented in practice, since it may sacrifice some drivers' interests, conflicts with their selfish nature, so that they won't be willing to follow. In addition, centrally calculate a system optimal route for all drivers induce high computation load, which makes it difficult to be implemented in real time for navigation services. In recent years, scholars have also studied the so-called user-oriented equilibrium routing, in which they use coordination or information provision to reach snapshot traffic equilibrium. For example, instead of independently choosing route, drivers now can share their routing preference and jointly decide their route choice. In this way, it reduced the overreaction and flash crowd effect in independent routing. However, it is still away from system optimal routing, since system performance is implicitly considered. In terms of system cost, though commonly used independent routing is the worst, UOER is better, and system optimal routing is the best. In this project, we proposed a correlated equilibrium routing mechanism to provide better system performance than both IR and UOER, while still comply with individual driver selfish nature without using externalities like pricing or tolls. And the distributed solution algorithm distributes the computation load to every individual driver's cell phones so that we can conduct the routing mechanism efficiently in a real-time fashion. Our routing mechanism can be implemented easily based on current navigation services. The first two steps are just as usual navigation services, in which every driver just provides their travel information, quotes the current travel time, and generates an initial routing preference. For example, in this scenario, the driver now knows the current travel time of 3 candidate routes. Then, according to the independent routing mechanism, he will have a set of probabilities to each route. For example, 0.6, 0.3, and 0.2. These probabilities are used as the initial routing preference. The difference lies in the third step, in which a central planner will then design a suggested routing preference for each driver that minimizes system cost and ensures they will be better off by following. So also in this case, in this example, the driver will now receive a suggested routing preference of 0.4, 0.3, and 0.3. So how to achieve such a result? This is achieved by finding a minimum system cost correlated equilibrium. A correlated equilibrium is a more general concept than the Nash equilibrium, in which a trusted agent will suggest action to each individual player so that they according to a probability distribution, so that each player will have no incentive to deviate from the suggested strategy. The mathematics seems to be difficult, but the intuition behind the concept is relatively simple. So still use this case as an example. Now the driver receives a suggested, the suggested action for a driver is to follow the suggested routing preference of 0.4, 0.3, and 0.3. And under the correlated equilibrium, it is ensured that they will not be better off by deviating from the suggested routing preference and follow their initial routing preference. We want to achieve a specific correlated equilibrium in which every driver would be willing to follow our routing mechanism. This is achieved by assigning a rationality constraints for each traveler in the form of this formulation, where the left-hand side is vehicle with utility if following our routing mechanism, and the right-hand side is the vehicle with utility if unilaterally deviating from our routing mechanism and sticking to its initial routing preference. Sorry. But the rationality constraint ensures that the expected utility of an individual driver would not be better off by deviating, so they will have no incentive to deviate. There are always multiple correlated equilibriums existed in a game, and our goal is to find the one that minimizes the system cost. In this study, we investigate the minimization of the expected system travel time. So by adding the rationality constraints for each vehicle and the standard conservation and positiveness constraints of decision variables, we have our mathematical program model for our routing mechanism. The solution of this MP will yield the suggested routing preference for each driver that minimizes the system cost and ensures they have no incentive to deviate. The MP is a nonlinear, non-convex constraint optimization problem with large size of decision variables and complicated, highly coupled rationality constraints. This characteristic makes the MP hard to be solved. However, an online navigation services needs fast computation speed. That's why we are motivated to develop a solution algorithm. In our distributed solution algorithm involves 3 parts. In the first part, we use Augmented Lagrangian to relax the rationality constraints. In the second part, we distribute the computation load to each individual vehicle. And in the third part, we designed a customized projection algorithm to conduct the calculation efficiently. So in the first part, we just follow the Augmented Lagrangian framework and use penalty and Lagrangian multipliers to relax the rationality constraints into the objective function. And the problem is changed to the subproblem MPAL. And by changing the first item in the MPAL from link-based to path-based, the subproblem can be reformulated as a separable problem. So now the objective function of MPS, is fully separable among each user. So it can be expressed as the summation of each individual vehicle's objective function. And to solve the transformed subproblem, we usually iteratively update the solution using the gradient of the objective function, and then conduct a projection to the remaining constraint space. To do the computation effectively, since the objective function now can be expressed as the summation of every individual's objective function, we can now let every vehicle calculate their own gradient information and then send back to the central planner. In this way, the central planner decomposes the computation load, and when they collect the result from the individual vehicle, the central planner can recover the full gradient it needs to do the solution update. And the last step, after the solution is collected, after the calculation results from individual vehicle is collected, we need to do the projection. Since the subproblem still has some constraints. The constraints, however, is in a specific structure, which is of a epsilon probability simplex. So based on existing algorithms, we developed an epsilon probability simplex projection algorithm that could conduct the projection efficiently. Our routing mechanism and the solution algorithm can be implemented as an app on drivers' mobile devices, on drivers' smartphones. So in the first step, the drivers just provide their travel information through the app to the central planner. And the app for each driver will estimate their initial routing preference. The CP then, based on this initial routing preference, will calculate the suggested routing preference by solving our mathematical programming model, and then send the suggested routing preference to each driver's app. The app will then generate a suggested route for the driver according to the suggested routing preference. We conducted the numerical experiment in the SU4 network to validate the effectiveness of our routing mechanism and the computation performance of our solution algorithm. The first figure shows the computation time of DAL compared with a commonly used MATLAB solver. The orange line is the computation time of our solution algorithm under different number of vehicles. And the blue dashed line is the computation time of a MATLAB-based solver. It can be shown that the DAL outperforms SQP in all scenarios. And it could solve a scenario with 1,000 vehicles in around 10 seconds, which could satisfy the fast computation need for an online navigation service. The second figure compares the system performance of our correlated equilibrium routing mechanism with independent routing and user-oriented equilibrium routing. The left-hand side is the system cost reduction compared with independent routing, and the right-hand side is the system cost reduction compared with UOER. It can be seen that the system cost could be reduced by around 55% compared with independent routing, and approximately 3.6% compared with user-oriented equilibrium routing in the scenario in a congested scenario. The third figure shows the impact of CERM penetration rates. So we conduct the experiments with a total of 1,000 vehicles, and the vehicle that participates in the CERM ranges from 100 to 1,000. It can be, the blue bar is the system cost when there are CERM vehicles, and the orange bar is the system cost when all vehicles follows the independent routing. It can be seen that as the penetration rate increases, the effect of CERM to reduce traffic congestion and system cost will become more obvious. And under every penetration rate scenarios, to evolve CERM will be better off than not involving. And the last experiment demonstrates the convergence robustness of our solution algorithm. So what is robustness? Why do we need to study that? So in real world scenarios, when we conduct a distribution process, the vehicle needs to, the smartphone on the driver needs to communicate with the central planner. And in real world, the wireless communication may not always be stable. So we study the scenario when each individual vehicle will have a random probability to be disconnected with the central planner. And the result here shows the computation time of DAL to reach a result under different connection probabilities, ranging from 0.8 to 1, which means that a vehicle has 80% of chance to be well connected. It can be shown that although the computation time increases a bit when the connection probability decreases, but it will still guarantees to converge under different connection probabilities. A summary for the project. So for the correlated equilibrium routing mechanism, it helps drivers find routes that satisfies their interest without using externalities. And at the same time, it achieves better system cost than the commonly used independent routing and user-oriented equilibrium routing. For the solution algorithm, it takes advantage of individual vehicles' computing power from their smartphones, and it could converge well and fast enough for online navigation services. Okay, thank you. You are free to ask questions here to both me and to both me and Rupa.
I think we have a couple of questions in the chat. I'll address the first one. I believe that nudge theory can be used to increase connectivity, especially in the context of mode choice. If we are looking at bridging certain connectivity issues in a region, but this study does not consider that. It purely considers route choice in the context of personal car travel. But
Hi, Rupa. I think you can first read the questions.
Sorry. The question was, with land development patterns offering limited mobility, access, and connectivity, does the nudge theory include increasing connectivity to relieve congestion? I believe that can be done in the context of mode choice. This study hasn't considered mode choice. It only considered route choice, and specifically with personal car travel. But I think nudge theory can be expanded to that as well. I think the second question is to you. Did you study the total surplus or consumer surplus of system and across different demographics? Or maybe it's for me. I think it's for me. We did not consider the actual population demographics. We just assumed the user preferences. But to study this, we would have to explicitly have a user preference model within the training environment and understand the effects it has.
Thank you, Rupa. And for the third question, if this is a real-time system coordination application, does it accommodate rerouting due to incidents such as crashes and bottleneck congestions? This is a good question. So in the current project, when there is a need to reroute, for example, when someone changes route or there is incident occurs that changes the current traffic condition, our correlated equilibrium routing mechanism needs to be rerun again by using this updated travel information. So but it could still give a result in an efficient manner. Thank you, everyone.
Thank you.
In case you need to contact, here's the email address for both Rupa and for me.